Today we will go over section 4.2, which is critical points, local maxima, and local minima. So previously in chapter 3, we learned how to take maximum and minimum by taking the derivative of function and equaling to 0. We also said when the derivative of a function is undefined, that point has also the possibility of being a critical point where maximum or minimum occurs. Just to define critical point meaning again, it is a point in the domain where the function is either not differentiable or the derivative equals to 0. When asked, you need to provide both the x and y value for critical points. Now, we also have what we call critical numbers, which is the same thing as critical point, but only includes the x value. Or you'll see often represented by C, which stands for constant. Now, before diving into more, I want to clarify what is local minimum and maximum and how it differs from the maximum and minimum problems we did before. Maximum and minimum we identified before was the highest and lowest point on the entire function. So these are called my global maximum, which is the highest point, and global minimum, such as identify on this graph, the lowest point. However, local maximum occurs when at x equals c, if my fc is bigger than or equal to fx for all x near c. And similarly, local minimum occurs at x equals c, so x equals any constant if my fc is now smaller than or equal to fx for all x near c. So together, local maximum and minimum values of f are called local extrema. There are some things to note when identifying local maximum and minimum. So one of the rules that we can use to identify, sometimes local maximum and minimum can also be global extreme points. So let's say in this case, we have y equaling to x squared plus 1. And I know my local minimum, my lowest point would be at -1 right up here, right? However, I also know it's also the lowest value on the entire function. Therefore, it's also my global minimum. 2. Not every global maximum and minimum is a local maximum and minimum. So for example, in the function of root x, I know the lowest point on the function is when x equals 0 up here and y also equals 0. However, it is not my local minimum because root x is undefined when x is negative right up here, right? So it cannot be my local minimum. It's only my global minimum up there. 3. Not every local maximum and minimum is a global maximum and minimum. For example, in this graph, it's a function y equaling to x cubed minus 3x squared. Here is my local max. Let me use a different color. Here is my local max. And here is my local minimum. Right? However, neither of these points are global extreme points because the function keeps going down up here where my global minimum would occur, and it keeps going upwards where my global maximum would be found. In order to identify these maximum or minimum points, we use what we call the first derivative test. We do the same thing we did before, take the derivative of the function and equal it to 0. But now we use this to interpret if you have a maximum or minimum, right? So we use the derivative equal to 0 that gives you the exact point to your maximum or minimum. But another way, without having that point, to determine if I have a minimum or maximum is if you plug in any number and see that your derivative changes sign from, let's say, negative to positive at x equals a constant, then your function is going to have a minimum point because it starts to decrease due to it being negative, and it starts to increase, therefore I have to have a minimum. Same thing over here, if you have a maximum, then your sign needs to be changing from positive to negative, indicating you actually have a local maximum. So let's start with a problem. For the function y equaling to x to the power of 4 minus 8x cubed plus 18x squared, determine all the critical numbers. Determine whether each of these values of x gives a local maximum, a local minimum, or neither for the function. So what's different from the previous questions that we did, I don't have a graph or I don't have anything else given to me. It's only the function. In these cases, I can apply the first derivative test and just take the derivative of the function given to me and equal it to 0 to find the critical numbers. So if I take the derivative of my function, I'm going to apply the power rule to the x to the power of 4 to get x for x cubed. Same thing over here, keep the constant and then apply the power rule to the other one to get 3x squared. Same thing over here, keep your constant and then apply the power rule, which will give you 2x. So putting all these together would give me 24x squared plus 36x. Okay, so since I have my function now, I can equal this to 0, right? But before doing that, just to make it easier on me, I can take out x from the function. That's what I realized. But also, I realized the constants are multiples of 4. So I can also take out the 4 and to get 4x, and I'll put in brackets what I have left is x squared minus 6x and then plus 9. And this will equal to 0. Also, what I realized is I can actually simplify this right over here. And if I do that, I'm going to get 4x, x minus 3 squared equaling to 0. So now that I have everything, I can separate these two and equal to 0 to find my critical numbers like we did before. So now I have 4x equaling to 0, and I have x minus 3 squared equaling to 0. From 4x, I realize if I divide both sides by 4, I'm going to get x equaling to 0, so that's one of my critical numbers. For this one, I can take the square of each side. It's not going to matter for the 0, so it will still be 0. But now I can send that 3 to the other side to get the value of x equaling to 3. So I found my two main critical numbers. So from here, I know that my critical numbers are either the maximum or minimum points, but different from the other questions we solved, I don't know which one represents my minimum and I don't know which one represents my maximum. So for this, what we do is the easiest way to do is create a table. So the first thing I'm going to do is find the intervals. So what we mean by intervals is, let's say for the function given to me, I know that at x equals 0, somewhere over here is the point where I have maximum or minimum, where my derivative is probably going to change signs from negative to positive, like I said before. Same thing with x equaling to 3. Somewhere, I don't know if it's positive or negative, right? Somewhere along those lines, I'm going to have a maximum or minimum, which derivative is going to change signs. So as intervals, what I need to look at is what happens before I come to x 0. So to represent that, I'm going to say x smaller than 0. So I'm trying to find if it's increasing or decreasing at that point. Now also to determine, I need to figure out what happens between this points, right? Is it increasing or is it decreasing, right? So I'm going to say between 0 and 3, and that's my, oh, that's an ugly 3, and 3, and that's my other interval. Lastly, I'm trying to find what happens right after 3. So is it increasing or decreasing? Same thing. So I'm just going to say x bigger than 3. So I'm done with determining the intervals. The next thing I'm going to do is take the derivative and plug in a value that represents the intervals. So the second portion of the table is sign of the derivative. So I know my derivative is right over here like I found. To figure out what is the sign of my derivative when it's smaller than 0, literally plug in anything you want. So -5, -6, -7, anything that's smaller than 0 and not 0. So I'm just going to plug in for it to be easy, -1. When I plug in -1, I get the value of -64. It doesn't matter if you get a 64, 100, whatever. What I care about is the sign, because sign indicates it's decreasing when it's negative. So I'm just going to put a negative sign for this. Now passing on to the second interval, which is between 0 and 3, I'm just going to pick 1, right? It's easy. And when I do, I get a value of 16, and I know 16 is a positive value, so I'm just going to put positive sign. As for the last interval, I'm just going to put 4 and not make it huge numbers. And again, I get a value of 16, therefore it's positive. Doesn't matter if I put 4, 5, I'll get a positive value either way. Lastly, I need to put the behavior of my original function. So I know if I get the derivative sign as negative, my function is decreasing. So I'm just, to represent decreasing, I'm just going to put an arrow, but you can write decreasing. Same thing with the positives. So if I see a positive, it's increasing. So I'm just going to say my function is increasing for those intervals. So if you were to draw the shape of the curves, it will look something like this. So I'm going to put that into the graphs. I know when it's smaller than 0, I'm going to get something like, if I were to pick that value, so it would come to something like this. And then it starts increasing towards the 3, so it will be something like that. And it keeps increasing after 3 too, so just goes like that. So I can say that there is a minimum at x equals 0, so there is a local minimum. So that's, as an answer, you can just say x equals 0, there's a local minimum. For x equaling to 3, however, it's neither a maximum or a minimum. You see that it keeps increasing, right? So as an answer, it's neither for the function. Given the graph of polynomial function y equals fx, I need to draw the derivative of this. The only thing about this is I only have a graph. I don't have any function whatsoever. So from this graph, I'm going to draw the derivative. First thing I'm going to look for is the critical numbers, as it's easy. I know critical numbers occur at a point where it's maximum or minimum. So I know my local minimum is right up here, and my local maximum is right up here. I know at these points, if I were to draw a tangent, it would be horizontal. And horizontal just tells me that the slope of the tangent would be 0. And that just gives me the value of my derivative. So I know at those points, because this graph is going to represent the derivative, my y value is going to be 0. X values are the same though, so my x value is 0 at that point, and I know at that point my derivative would be 0, so I put it right up here. So both my x and y values are 0. Same thing over here, I have an x value of 1, so I'll just put 1 over here. And I know over here my y value would be 0 because that's the derivative, so I'll put it right up here. So now that I'm done with the critical numbers, what I'm going to do next is determine the intervals. So what's going to happen when I'm approaching my first critical number? So is it increasing or decreasing? I don't know that yet. So that's what I'm trying to find. So when x is smaller than 0, I'm trying to figure out what's my derivative. When it's between these two, I don't know what's happening, so I need to also find that another interval is between 0 and 1. And I also need to figure out what happens after, so when x is bigger than 1. So starting from x being smaller than 0, it will represent the function right over here. How I can find my derivative if it's increasing or decreasing, I can actually draw tangents to any point. You can draw it multiple, right? I know in general I have a tangent looking like this. And for that tangent, if you were to try to find, oh, is my slope negative or is my slope positive? So just by looking at it, I can just say negative, but if you were to go deeper, you can just put imaginary like numbers to this, right? So if I were to say this is x1 and here is my x2, right? And here is my y value, here's my y value. This would be my y1, this would be my y2. And I know when I take the slope, my formula is x2 minus x1 all over y2 minus y1. Now, if you realize y2 is smaller than y1, so therefore y2 is going to be a number that's really small, so I can just say like 1, let's say, and I know my y1 is going to be bigger than that, so if you were to say 5, I get a negative value. So either way, that's how I can actually confirm too. So because I get a negative value for the slopes, my function right over here would be decreasing. So starting from 0, I'm just gonna make it decrease. So it's just gonna go like that, right? So next thing I'm gonna do is determine what's happening between these two. So now on the graph, it's represented by right up here. So I'm going to draw tangents and interpret what's happening. So if I were to draw a tangent over here, it will look something like this. So I see that it's different than the other one, so it's increasing. But then, however, when I draw a tangent over here, it starts getting a little bit different. So just for visualizing it better, I drew it again just as like a bigger one. And if I were to draw a tangent, it's going to look something like this. So it's increasing, 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 and starts to decrease up here, right? So I know at this point, the value of the derivative would increase, and at halfway, it starts to a little bit decrease, right? And it's approaching to become 0 again, because that's where my local maximum is. So now, because it increases up here, so increases, and it starts decreasing up here, how I'm going to draw it on the derivative is going to be at halfway point, so 1.5, let's say. It's going to start increasing to that point, and then it will decrease to my maximum point, which is at x equaling to 1, and I'll get a half circle like that for my derivative. Now, the last interval I have when x is bigger than 1, which represents up here. So if I were to draw tangents again, it will look something like this, right? It's just going to go like that. And I know when we did the slope for something looking like this, we said it was decreasing, right? So it's going to decrease again as the derivative. So same thing as when x was smaller than 0. Let me make it same color. So yeah, your derivative would look something like this.